Good day, everyone. I'm here to give you one of your more fun and interesting sessions here at the Compute Memory and Storage Summit. I'm going to be talking to you about optimizing content delivery to network design. I'm Andy Banta, and spent about, quite a few years in the storage industry, and quite a bit of my work has been on storage networking, specifically fiber channel, iSCSI, and other various different storage protocols at a variety of different fairly big companies out there. Uh, Currently, I'm doing some work for Magnition, and Magnition is a small but established company that works on uh, problems with data placement, uh, how to handle hierarchical memory and storage sharing, how to minimize latency, optimize for cost, all of these various different pieces. We have a handful of award-winning papers throughout there. We have a load of patents on this technology. We know what we're talking about in terms of dealing with hierarchical storage and memory. Let me start off a little bit by talking a little bit about engineering and all of the engineering disciplines out there: electrical, chemical, mechanical, civil, bioengineering. They all use computers and use simulations to solve their problems. Nobody goes off and builds a chip from scratch. Nobody goes off and builds a car from scratch. They all build these in simulation and simulate all the various different things that could be going on with them. Isn't it about time that we started doing this with software and system design? Right now, software and system design is largely seat at the pants, sit down, try to figure out how to make things work. What Magnition is trying to do is convince people that you really should be doing engineering simulations on your software and system design. So let's start off with, since you're mostly storage and storage networking people, let's start off a little bit with what is content delivery. I'm not going to spend real long on this, just a quick overview. The idea that you have users somewhere in the world that are interested in getting to content put together by a content provider. And these could be various different places all over the world or all over a certain geolocation. They're all trying to get to the content their content provider has. And for, if you don't know what I'm talking about, for a content provider could be somebody who, streams movies or has a picture repository or a news organization or someplace you download software. All of these various different things are content providers. Now, the whole idea of this is that as a content provider, you're introducing a bottleneck at if everybody directly connects to the content provider. There's no way that you have the ability to maintain collections from all of the various different people directly to a content provider. This is where the idea of content delivery networks come in. The idea is that you have a network that covers all the global or all the geolocation areas that you're interested in covering. And this is connected to the content provider to distribute the content. In this case, you would typically connect to the network in the closest location to you. This is not a new idea. Akamai is kind of the granddaddy of all of the content provider networks. They've been around for 25 plus years. And since then, there have been quite a few new ones that have come along. We have AWS CloudFront, we have Cloudflare, and the telcos are getting into it as well. Verizon and British Telecom are considered content providers today as well. When we talk about a content delivery network, it's not really just like a mesh that's out there that everybody connects to. What the individual users are connected to are points of presence on the content delivery network, otherwise known as POPs. And there are going to be various different POPs around the world. And this is how you as a user would get to this content that's being provided by the content provider. So you're probably asking yourself, what the heck does this have to do with compute, memory, and storage? Why am I talking to you about content delivery networks at a compute, memory, and storage summit? So the whole idea of this point of presence is that you have a load balancer where people come in and things get spread out, and on the backside, it connects up to a content provider. In this, you'll have a bunch of servers or compute resources. And it could be just a couple servers, or it could be quite a few. It could be hundreds of servers. It largely depends on what type of content provider, content delivery network you are, and what type of content you're delivering. And each one of these, or commonly, each one of these servers is going to have some memory associated with it. And the memory would be used to cache some of the content that you as a consumer would pull down. And there's going to be uh, there's potentially going to be SSD content in there, or storage components in there as well as a second level of cache. This is a fairly common configuration for content delivery networks of having servers with multiple levels of cache. Now, how do you go about optimizing this? Well, I mean, some of the ways that you could go about optimizing this is just vary the number of servers you have. That's a step one on trying to optimize this. You could also vary the size of the components in them. So you could say, let's try less DRAM and more SSD, or let's try more DRAM and less SSD. Or what do you know? You might say that not all of these servers actually need to be both levels of cache all the time. Maybe some of them are just one level of cache and some of them are two levels of cache, or some are one level of cache and the others are the other level of cache. And then you get into more interesting questions, like if you have a bunch of servers and they all have storage in them, is that storage distributed, or does each individual server have its own storage that it's using to cache the information that would be interested? Do they have their own, or would they all potentially be distributed and linked together? And this is a kind of valuable or important decision to make because it really changes the algorithm that you would use to uh, to do your load balancer. If your load balancer says, "Oh, uh, this server is going to have this content stashed," you would want to direct the requests to that server. If all of the servers are connected together and have a shared cache, you can pretty much tell the load balancer to point it at the most likely used one. So let's get back to our original thinking here. There's also some different ways that you could use the cache. You could say, the most commonly hit stuff will go into our DRAM, our high level cache. And you would do this because you want lower latency. You want the users to have to wait less time to get their content. And that's one philosophy you could go about take on it. The other philosophy you could take on it is that you put more commonly hit stuff into your SSD. And the reason you would do this is you don't want to necessarily be evicting things from your SSD. You don't want to be throwing stuff out from your SSD all the time. It's going to do write amplification and screw up the wear leveling on your drives. And it means that things that are only getting hit once would potentially be in DRAM. And once it's hit and you realize that you never need it again, it can get thrown out at some future point. So this is where we get into places where we're not playing with the hardware of it, but we're playing with the algorithms that exist inside the POP. And so in this case, we can play around with the algorithms that we use for demoting and promoting items between the caches. We get to play around with the algorithms for allocating stuff into the cache, or the eviction algorithms that are used in each one of the caches. There's all sorts of variables that you can use. And it's to come up with the best uh, content delivery network, you need to optimize this. And this turns into an optimization nightmare. You have loads of variables. You have far more variables than anybody can sit down and figure out. You don't have the ability to look at all the variables and wring the best answer out of that towel. So this is where we're trying to take a different approach. We built a framework that allows you to build simulations of complex memory storage systems. In this framework, you can plug in various different components, either ones that we have a library of components that are already out there, or you can plug in your own components. And then once you plugged in the components, you can move them around, interconnect them in different ways, provide a reasonable number of constrained variables to try out various different things. And the most important thing with our framework is you can run these against genuine IO traces. So you can run it against the benchmark as well, but the preferred method would be let's run it against a real workload. And to give you an idea of how these components might fit together, for that simple two-layer cache that I was just talking about, if it's a content delivery network, chances are the request is going to come in as a URL, and the first level cache would, hook up through to DRAM, and the second level cache would hook up through SSD. What we do is we simulate each one of the blocks in the upper portion of this, and simulate the amount of time that that component would take to complete its job. The cool thing about our simulations are that we don't need to store the actual information. All we need to do is simulate the amount of time it takes for that operation to complete, and we come up with the optimization for best speed or best performance. Similarly, we have broken down the pieces inside the cache and modularized those and allow us to plug in different algorithms for allocation, lookup, and eviction as well. So what have we done with this for content delivery networks? Well, right now there are a couple cloud delivery networks out there that document their architecture and provide traces to be able to see what they're doing. The ones we chose to play with were Cloudflare and Wikimedia. We were able to go and get genuine workloads from each one of them. These are anonymized HTTP traces where we can't actually tell who's making the request, but we can use it to build out the cache. And we did a whole bunch of variants on the baseline from what the papers said they were originally doing. We changed the number of caches. We changed the various different algorithms for promotion, demotion, eviction. We changed the sizes of the DRAM and SSD. We changed load balancer algorithms. All told, we ran 125,000 different variants, each against a day's worth of traffic. We did this in a matter of a few weeks. This gives you an idea of the power of simulations. We ran 125,000 days worth of traffic in the matter of a few weeks. So how do we go about doing this? Well, in the framework, we simulate each one of the components, and the configuration for it is really very simple. All we really need to do is say, here are the differences in the way that they're configured. And in this, you can also see there's some cases where we have, variable sets of lists of things. And these are the variants that we choose. And this is how we ended up with 125,000 different variants out of all the various different combinations. And the end results show us that for Wikimedia, the little red dot is the baseline that we got with their initial configuration. And the blue bars represent the performance results we got when we ran with our configurations. In this case, lower numbers in the graph are better. The bit miss ratio is the number of times that you're missing bytes. I'm sorry, the byte miss ratio is the number of times you're missing bytes, and you actually need to go off to the origin to get them. One of the important reasons why you want to be able to get hits is sometimes the origin is around the world, and sometimes the origin is very latent, has high latency. An example of this is if you go try to look up a video for like the Storage Developer Conference from 2020, it's going to take tens of seconds for them to load the video because it's not going to be cached on something that's local to you. And chances are when it gets all the way back to YouTube, they're going to have to go look it up in cold, slow storage. Similarly, with Cloudflare, you can see the baseline, and with Cloudflare, you can actually see that a bunch of the configurations that we tried are worse than the ones that are baseline. But the important thing here is that you can see that there are configurations that we ran that are better than the baseline. So to demonstrate this a little bit further, let's take a look at some of the variants that we ran. And for Wikimedia, the dashed lines are the baseline. Um, the blue dashed line is just the straight baseline for the byte miss ratio, and the red line is the um, normalized cost variant. So in this case, we're saying that different sizes. We ran different sizes than what Wikimedia and Cloudflare said they would, and if you normalize the cost of the sizes that we ran compared to what they would have, it changed them. But you can see that in all except the minimum cost case, we have a lower byte miss ratio than the baseline, and this for both Cloudflare and Wikimedia. And part of what we did here was we played around with the eviction algorithm. We have an intern recently who has put together a research paper on some new eviction algorithms. This is the link at the bottom of the screen, and she's working on a research paper reflecting the information that I just talked to you about today. So that should be available, and hopefully we'll be talking about that more at the SNIA developer or the storage developer conference this September. Just so you know, Magnition has proven results here. We've worked with a large storage vendor in the past, and when before we started working with them, they were doing about 2 experiments a day. And once they started using our simulation framework, they were doing 50,000 plus simulations a day. And over the course of our several-month engagement with them, they ran over 1 million simulations total. Now, this is a shipping product that's out there in the world today, and the results we showed were a double-digit performance increase in the latency, in improving the latency on these systems. What it showed you in the previous slides showed that we are getting similar results with the content delivery networks as well. So I hope you found this informative. Please do the survey on this. I appreciate any feedback I get, and thanks for your time today.